Okay, looks like everything is all set for a timely start for our second lecture of the day on high resolution shock capturing schemes for non-relativistic hydrodynamics. So I think all the online participants have already joined. So Kenta, we're good to go.
Okay, hi, good morning. So welcome back to the second lectures for the numerical hydrodynamics. So today's target or today's subject is to learn how to construct a scheme, numerical scheme, to capture the shock in non-relativistic hydrodynamics case. In particular, so first I'm explaining a very crude but robust method to capture the shock, but it's not good enough, not accurate enough to simulate in scientific situations. So we have to do, make a high resolution or high accurate capturing scheme, which is called a high resolution shock capturing scheme in fluid and non-relativistic hydrodynamics. So tomorrow and the day after tomorrow, we jump into the relativistic hydrodynamics, but the basic is very similar. So I want to start from very primitive part. So let's start from the short summary of the lecture one yesterday. So for non-relativistic fluid without gravity, so the Euler equations, continuity equations, and energy equation is written in this conservative form, right? And this is a conserved quantities and density, momentum, energies, and this is a flux. In the absence of the source terms, and by integrating this u bar, vector u in volume, this term is given by the surface flux terms by using the Gauss's theorem. Then you can prove that if volume is large enough and there is no flux at the boundary, you can prove that the integral of these forms are completely conserved. This is why we call this a conservative form, right? So, but as I explained yesterday, so if the shock or discontinuities appears during the evolution, you cannot apply the direct finite difference method to evolve this system. So in that case, we need to seek a weak solution by integrating these U bar, and then this weak solution results in the Rankine-Union relations, which the physical quantity should satisfy the before and after between the discontinuities. This Rankine-Union relation is given by this characteristic speed lambda and parenthesis u, which measures the difference between the before and after the discontinuity. Also the parenthesis f. This is the difference in the flux as well. So we studied that in this system, I mean the non-relativistic Eulerian system in 1D. So there are two characteristic speed. One is rho 1 u minus gs and u plus gs. So the lambda 1 and lambda 3 describe the expansion, the fraction wave, or compression or shock waves. And lambda 2 is described the contact discontinuities in where the density has discontinuity, but the pressures and velocities should be continuous. So we also learned that the Riemann invariance when we are cross the waves given by the light eigenvector values and Riemann. Sorry, this is a generalized Riemann invariant, and this is a Riemann invariant along the characteristic curves. And these quantities and these conditions are essential to construct the exact solution for the Riemann problem as you solved in yesterday. This is a short summary of the lecture one. So now, at least for the solved problem in a specific initial condition, you have learned how to construct the exact solution Riemann problem. And this is in general called the Godunov method. So we know how to construct the exact solution. So you may consider that we don't have to do a simulation, right? But as I explained yesterday, so there are several possibilities for the solution of the Riemann problem, depending on the initial condition for the left and right state. Yesterday, you just solved one specific solution, one specific initial condition. In general, there are a couple of those possibilities. One is maybe two rarefaction wave appears plus contact discontinuity and with or without vacuum. Then the second possibility is two shock waves propagating outward and contact discontinuity exists between them. And three is one shock and one rarefaction plus discontinuity, contact discontinuity. This is the sort of problem is representative of this situation. But you have a choice, you have the freedom for the propagation directions. So yesterday, given the initial condition I explained, you have a left propagating rarefaction wave and right propagating shock wave. But this direction is determined by the initial conditions in your simulation. So we have the freedom for the propagation direction. Maybe you may have a right propagating rarefaction and left propagating shock in your simulations. Also, there is a possibility for a vacuum state, which means if you start from the vacuum, it's going to be the vacuum as well. Or you may have a rarefaction vacuum, and you have also freedom for the propagation directions. So to solve that, okay, given the general or the arbitrary initial condition, and solving the Riemann problem exactly, so you have to take into account all these possibilities in the simulation, which means that computational is very, very expensive because you have at least 5 or 6 or 7 cases. And as you have already, you have noticed in the yesterday lecture, even for a specific case, you need to solve the nonlinear finding to get the P3, the intermediate state of the pressures. It takes a time, right? And so it is computationally infeasible to solve the Riemann problem exactly in the scientific ground or in the simulation. So which means that we have to develop an approximate Riemann solver is necessary to from the computational point of view. This is a target for this lecture too. So I want to explain how to solve the Euler system, but before jumping into the Euler equation or the system equation, we call it the system equations. Before jumping into how to solve these system equation numerically, I want to start from the super simple scalar equations given by these equations. U is in this case U is just a scalar field. It doesn't describe the velocities. But here is here's the equations, and A is for the simplicities. Now A is a constant and the positive case. So the solution of these equations is of course given by these equations for arbitrary function over f, which should be the argument variable should at minus x, right? If you plug this one to this one, you get this solution. You can confirm that this is a solution for exact solution for this equation, right? This is a super simple equation. But I want to ask you how to solve this equation given the discontinuous initial condition. For example, here is a schematic picture for the scalar field U as a function of the x, and that red dashed curves the initial profiles. So you have a discontinuity at x equals 0, right? It's a step function. If you start from this initial condition, exact solution tells you that if f(a) is a positive, this profile advect to the right directions, positive directions, right? So the blue curve is t is exact solution after a certain period, and this profile should propagate, should advect in the right directions. Do you know how to solve this numerically? So let's try to solve it by just directly the discretization system. The most simplest way for the discretization is a first order in time and second order in space. So in these lectures, I always give the n as the discretization in the time directions, and I is indexed in the spatial directions. So if you have time diagram, space-time diagram. This finite difference means that you discretize a space like this, and also in time like this. So grid index I describe that discrete point and n specified this time slice, right? So then you evolve from to here according to that the equation. So the direct discretization is just first order in time, which means that UN+1 is a grid of the here, and UN is a grid here, and delta t is the time step between the two time step, and also the delta x u here, discretization in the space is given by these equations. By using the Taylor expansions for here and over here and over here, you can get this discretization gives you that this form plus some truncation error. This is the basic of the finite difference. Anyway, so this is a straightforward discretization. Then, so if you put the initial condition given by lead profile, what's going to happen? Here is a result for us. Here is a very simple experiment. And the solid curve is the exact solution, right? Propagating to the right. However, the green blue point is the numerical simulations result. As you can see, obviously, this doesn't make sense at all, right? So you have many oscillations. So finally, it blows up and the simulation crashes. This is why. So to get the this is a exponential growing functions, and then so to analyze this same is stable or non-stable, the von Neumann analysis is a useful tool to predict that which time step we should consider to suppress this kind of instabilities. So this gives a relation between the delta t and delta x. And nu is defined by a times delta t delta x. And to satisfy the stability condition, this Coulomb-Friedrich-Lowry number, CFL number should satisfy some certain condition. However, in this scheme, by doing the von Neumann analysis, you can easily prove that this scheme is unstable for an arbitrary value of the CFL condition, which means that you can't do that simulation with this scheme. So what should I do? What should we do? So I'm explaining that the concept of the finite difference by the simple scalar advection equations. But the essence for the numerical hydrodynamics is a concept for the finite volume method. As I drawn in the blackboard, so I discretize the grid point by the circles or triangles. But the concept for the finite volume is introducing the cell. So here is the circle, field circle is a representative the grid point. But this grid point is consists of the cell, right? And in the between the two the cell, you have a cell interface, which is denoted by the I-1/2, I+1/2. I is a grid index in the spatial direction. Then, so if you define the volume average U by I in the cell of the here, so you can define like this. But of course, you have to assume some distribution of the solution inside a cell. But anyway, you can define the cell volume average like this. So then, so we integrate the basic equations inside this cell. So here, the first time just gives you the time average of U bar. But the second terms, A is a constant, so you can put it inside the partial x, and then so by using the Gauss theorems, and you can write down something like this. Okay, does make sense? Because delta x parenthesis AU integral dx mean that you have a surface fluxon, cell interface fluxon here and here, right? This is a exact, the transformation. I don't use any the finite difference or the approximation to get this expression. So this the equation tells you that the numerical flux at the cell interface should given by this expression. Okay, so the essence of the finite volume method relies on the conservation equations, also the finite volume method, which rely on how to evaluate the numerical flux at the cell interface. Conventionally, if F itself is called a physical flux and F tilde is called a numerical flux, which depend on the scheme you want to apply to solve the system. So let me repeat again. So the essence is how to evaluate a numerical flux F tilde in your simulations. Yep.
This is the last expression. Last expression is it like U or U bar?
Sorry, this is U bar. Yeah. Wait. This is a U. U, but U at the interface. Yeah.
Okay.
But I will explain how to construct the U at the interface. Right. Yeah. Not U bar. Because just simple. So you have delta x AU. This is a fluxon, and you integrate I minus 1/2 plus I plus 1/2 dx, right? Then so you just here at the here. Yeah. Yep.
Physical flux is AU. The physical flux.
Physical flux is F. Physical flux means that F means in this example A times U. A times U. Yes. Okay. Okay. So here is one example for the finite volume method. So, but in this example, I assume that A should be the positive. So let's generalize to the A is negative or positive, because we don't know a priori the sign of the propagation speed in actual situation. How to do that? So we can define the numerical flux by something like this. This is an arithmetic average of the physical flux of Fi plus 1 and Fi. And also the absolute value of the propagation speed times Ui plus 1 minus Ui. This is everything is a physical quantities, not a volume average quantities. So for example, let me take the one case. A is a positive case. So in this case, the A is positive and F is A times U, right? So then this term and this term is cancelled out. And then, so the numerical flux F tilde is given by this equation. This is this is a U bar, not U bar. Okay. Also, the flux at the cell interface I minus 1/2 is given by the AU bar at I minus 1. Okay. Then, so if you plug this expression to this scheme, what's gonna happen? So you get like this. So what's meaning of this finite volume discretization schemes? So we start from the discontinuity given like blue profiles, and let's suppose that here is a grid index I, and the neighborhood in the negative direction is a grid index I minus 1. Oh, sorry, this is the J or J minus 1. Anyway. This should be the I. I'm mixed up. But the meaning of this this expression means that U bar at I is updated by the information at previous slide of the U bar I and U bar I minus 1, right? For the positive case. As I explained, the positive A means that this profile propagates the light directions, which means that you only use the information from the propagation, the information, right? Because the information comes from the left to the right. You only use the left, the state to update the grid index I. This is the meaning of these equations, right? For negative case, what's happened? It's exactly the same exercise. Fi plus, because A is a negative right now, and here is this terms and this term is cancelled out. Then so you get F tilde I plus 1/2 is given by Fu bar at I plus 1. And also the F tilde at I minus 1/2 is given by the Au bar at I. If you plug this expression to the numerical scheme you have developed, you get this expression. The meaning of this this discretized form is the same for the positive A case. So you have the discontinuities, the initial profile, but because of the negative A, this profile is propagated to the left directions, and this equation means that you use only the I plus 1 and I information at I and I plus 1 to update the grid point I, right? So this is called the first order upwind scheme because you only take into account the information of the upwind. This looks like very physically correct because you only take into account the information which comes from the propagation direction of the systems. So what happens if you apply this scheme, with this continuous, the initial profile? Let's see. Here is a plot. Again, and the black is the exact solution, and blue curve is a dotted the numerical solution. How do you think about this figure compared to this one? Which is good? Which is better? Yeah, of course. Very simple, the scheme, but it looks very physically correct, right? It not sharply, but it captures the discontinuity without oscillations. Anyway, the oscillation is always an obstacle for the numerical simulations. So there is no oscillation essentially. This is a good point. But there is the drawback, like initial discontinuity is a sharp one, but it's a little bit smeared out. It will be helpful. Can you do that? Okay. So let's explain why this smear out happens. So suppose that the profile is smooth, then so you can apply the Taylor expansion even for a finite volume method. So let's evaluate numerical flux at I minus 1/2 here by Taylor expanding at the grid point I. Then so you can expand, of course, Au bar at I plus the flux plus the truncation error. So which means that if you plug this expression to this one, you can estimate the truncation error, which determines the accuracy of the solution. Then you can get the truncation error is the first order. First order means it depends on the power delta x of power unities. How to eliminate this? Okay, good. So the first order upwind scheme looks to be a good tool to physically correct answer, but the accuracy is not good enough. So the next task to find a high order accurate scheme to capture the discontinuities. So let me introduce the concept of the monotonicity preserving. This monotonicity preserving means that if a function of u is a monotonic in x for a given time slice, like here, it is also monotonic in x at the time next steps of the tn plus 1. Roughly speaking, so monotonicity preserving means that you do not allow to increase the oscillation in the numerical simulations. So any hydrodynamics scheme should guarantee the monotonicity preserving property. Otherwise, physical oscillations, like example I showed the first time, will appear. Then so the simulation crashed. However, there is very strong theorem which is called the Godunov theorem. This statement, the statement of the Godunov theorem is that any scheme higher than second order, which has a following form, cannot preserve the monotonicity where bk and KL is a non-negative integer. Here is a scheme. So the profile of the ui at n plus 1 here is determined by the linear combination of the s slice n, right? K runs from some integer KL to the KL, and the bk is a sum constants. So which means that this linear form of this, you cannot construct the second order or higher order scheme which preserves monotonicity preserving in this form. Let me prove. So by calculating that just delta ui n plus 1 is defined by un plus 1 I plus 1 minus un plus 1 ui, then so of course you can easily calculate this equation, right? So that monotonicity preserving means that if delta uni is greater than 0, delta un plus I should be greater than 0, should be satisfied for any arbitrary value of the I, right? This is a monotonicity preserving. So let's consider the case in which the some value of the bk0, bk naught is negative for a particular value of the k naught. Then, so if the delta uni equal 0 is satisfied except for some certain value of the k1, by plugging the this I equal minus k0 plus k1 case, in this equation you can easily get you can easily calculate this equation. By these conditions, the only term is a bk naught times delta uk1n, right? So, which means that these terms has a sign opposite to this terms because of this condition. bk0 is a negative, right? This means that violating the monotonicity preserving, which means that to guarantee the monotonicity preserving, bk should be greater than that, therefore all the value of the k. So let's consider this is a requirement from the monotonicity preserving condition. Monotonicity preserving condition. So let's seek the truncation error for the scheme of this form we applied in this example by using the Taylor expansion around the u equal n and u equal I. You can write down this equation like Taylor expansion like this, but UTL means one time derivative u and else time in space. UXL also this expression L plus 1 times of the spatial derivative, right? And by using this Taylor expansion, and you can get this solution. You can get solution. So the truncation error determined by this residual error, right? So the truncation error disappears if SL is defined by sum of these terms. It is equal to minus nu power of the level. My nu is a CFL number as I explained here. It gives the A times delta T over delta X, right? So by plugging this expression here, so to cancel out these two terms, you need this condition, right? So therefore, the piece orders, the accurate scheme in space and time holds if and only if the following conditions are satisfied for arbitrary for the value of the Q. Well, okay, let's consider the second accurate the scheme. Second accurate means the P should be P should be 2 and K round from 0 to 2, right? So S0 is going to be 1 unity, and S1 is going to be minus nu, and S2 is going to be nu square. However, on the other hand, S square is given by K, sum of K in terms of K square be K. You can easily rewrite this equation is something like this. This is a super simple one. But it gives that this term is S1 and this term is S0, right? So because S1 and S1, we know the value of the S1 and S2, this gives this equation, okay? Just plus nu square, which means that for the non-negative, for the non-zero value of the BK, this terms becomes the positive. This expression should be greater than nu1, nu2, because of this condition, right? So to satisfy this condition, the first term should be zero. This is the meaning of the monotonicity preserving and the higher order accurate scheme. So the equality for the last expression, this expression only for the useless case. I mean, BK is 0 for arbitrary value of the K, which means that if BK is 0, which means that you don't evolve this equation, right? So this is a Godunov theorem show that there are no monotonicity preserving linear scheme of this form, right? That second or higher order accurate. This is a very powerful, the theorem. So what should we do? So to see that this expression, so let's consider that Lax-Wendorf scheme, which is second order time and space. In Lax-Wendorf scheme, the UN I plus 1 or flux is given by please multiply the A this term, and then so the flux is given by these terms and these terms and these terms. So let's solve that initial discontinuity propagation problem wise. Let's Lax-Wendorf scheme. Then so you have oscillations because this is a second order. So Godunov's second order. Also, this is a linear and linear combination of UI, right? So this scheme is written by like this. So this is a proof for the Godunov theorem. So you have oscillation and physical oscillation for the second order time and space Lax-Wendorf scheme. So the hint is if you assume the linear form of this linear combination of UI given by this kind of stuff, you cannot avoid physical oscillations. So which means that we need a nonlinear scheme. So the hint is a nonlinearity. So let's consider the first order upwind scheme, which I have already proven a very stable, but not super accurate. And also the second Lax-Wendorf scheme, which is accurate, but it's not robust to capture the discontinuities. So let's update U bar I and U bar I at n plus 1 by these equations. It's just physical, the numerical flux F tilde I plus minus 1 over 2. So for the nu equal the positive nu case, which means A is a propagation speed is a positive case, F tilde is upwind scheme and F tilde also the Lax-Wendorf scheme. So let's combine these two methods appropriately. How should we do that? Sorry, this is similarly the A equal negative case, nu is a negative case, and introducing the limiter function B I plus minus 1 such that Lax-Wendorf scheme is reduced to be the upwind scheme at the discontinuities by plugging something like this, right? Here's, okay. Sorry. Yes. Something like this. Then, so for the positive case, positive new case, the numerical flux is given by these terms plus some limit function. And if bi plus 1, 2 is a function of u I plus k, with k is some integer, which means that this scheme is a nonlinear in terms of the ui. This is circumventing the Godunov-Seal. The next point is how should choose this functional form of the bi plus 1 over 2. To do that, let's calculate the monotonicity preserving condition by plugging the by calculating the un plus I minus un by plugging this expression for the negative for the positive new case. For negative case, you can easily get this equation, right? So it's a messy expression, but it's a straightforward calculation by plugging this one to the to here, right? Then, so you can find for the positive case, you have this expression. For the negative case, for this expression. So for the positive case, if you divide un I minus 1 un in the both side, you get this expression, right? And also, if you divide the un I plus 1 minus un in the negative case, you get this expression. And where the Ri introduced here and here, it's defined by this equation. It is just a difference between the I plus 1, I minus 1 cell, right? So a sufficient condition to suppress the numerical oscillation is given by this quantity is in between 0, 1, and 2 for a positive case, and these quantities should be between the 0, 1, and 2 for a negative case. What the meaning of these equations? So here's a schematic picture for the propagation for the profile. For the positive case, you have an initial profile for the n, and it propagates to the right direction for the A is called positive case. And not anybody. Please provide. Okay, so the meaning of this these equations mean that here un plus yi minus un un plus yi minus uni is between the difference between ui minus 1 and uni, which means that this amplitude here is not, it should not larger than these values. It doesn't mean that, it means that you don't have oscillation if this condition is satisfied. I think this is similar for the negative case. The profile is left propagating, and this if this condition is satisfied, this updated value that does not make oscillation in the simulations. So now we have a condition for a bi, which is which should be the nonlinear function for the uni. For the by plugging these conditions by this expression, you can get the B, it should be satisfied this condition for a positive value, and B should be satisfied for the negative case. The further simplification is possible if we only consider a sufficient condition for the absolute value of the nu is between 0 and 1, and this should be satisfied for to get a stable CFL condition. So then if you plug this condition to here and to here, this is a sufficient condition for the positive case, and this is a sufficient condition for the negative new case, right? And here you just take it nu to 1, limit to the nu to 1 or nu to 0, and here nu to 0 and nu to 1, right? So nu to minus 1, sorry. And this also this the condition is automatically satisfied if both equations, both conditions are satisfied, which means that bi plus 1 over 2 is between 0 and 2, and bi plus 1 over 2 times delta I over delta I minus sine u is between the 0 and 2. Why you have this sign? For a positive case, it's I minus 1, so this becomes 1 over Ri here. And for a negative case, here it becomes I plus 1, which is Ri here, right? So if you plug this condition to here, you can easily prove that this condition is enough to satisfy these conditions. So what lesion for this bi plus 1 over 2? So here is a schematic diagram for the bi plus 1 over 2 as a function of Ri. Ri is here, delta I minus 1 over delta I. Here's a schematic function of the Ri. So first condition gives you that bi plus 1 over 2 should be bound between the 0 and 2, right? In these two regions. And the second, the equations gives you that for the negative value, here is the bi plus 1 over 2 equal 2 over Ri case. This is a limiting case, right? So which means that if you want to satisfy this condition and this condition, the blue hatched region is a sufficient condition for the limit function of the monotonicity preserving scheme, right? The important point for the negative value for the Ri, it's bi plus 1 is going to be reduced to 0. What does it mean? Which means that this scheme is go to the upwind scheme because the second term is completely disappeared, right? So what's the meaning of the negative value of the Ri? Ri is defined by the something like this. Maybe let me confirm. Sorry, the other way around. So here is R ui n minus u n I minus 1 divided by un I plus 1 minus un. Right. So the negative meaning of the Ri mean that if you plot the x as a function of 5, something like this. Here is I, here is I minus 1, here is I plus 1. Negative value of the Ri means the sign of the here and here is different. So which means that you make the oscillation. So this should be avoided. Right? So this is the limit function automatically satisfy this condition. And if this kind of if the situation is going to disrupt this situation, so you cut off you reduce to the first order upwind scheme, which is stable in the shock discontinuities. This is a concept for the limit function, but you have a freedom to choose. You still have a freedom to choose a functional form of the bi plus 1 over 2. Here is a blue hatched region is allowed regions for to get the monotonicity preserving high order scheme. So one example for the flux limiter is called the min mod function, which is given by the argument value of b1 and the bri. So min mod function of here is given like this. When the absolute value of the bri is greater than 1, also the bri is positive case, it's going to be reduced to 1. So if the absolute value of the bri is less than 1 and bri is greater than 0, it's going to be the bri. Otherwise, it's going to be reduced. If you plot this functional form to this diagram, so you can get this red profiles, which satisfy the blue hatched lesions, and also the meaning of the B is given by this diagram. So we want to make the scheme as accurate as possible by employing the like a Lax-Mendel second order scheme, which means that the bi plus 1 over 2, it should be 1 in that case. So you have a control parameter for the b to control this point to here and here. And I'm going to explain which value of the b should be in the later on. But anyway, you have a freedom to choose a b. Okay, so now it's a min-mode function is a good limiter to describe to develop the high order monotonicity preserving scheme, nonlinear scheme. So let me explain the total variation diminishing TBD, which is defined by the difference between the absolute value of the difference I plus 1 minus ui and sum up from the I equal minus infinity to infinity anyway. So TB parenthesis UN is defined by these equations. So TBD condition is described by this inequality. TB at the UN plus 1 should be smaller than TB at the UN, right? So once the total variation, the meaning of these equations again, so you do not allow to increasing the oscillations in the numerical solution. So once the TBD scheme is employed, the monotonicity preserving property is guaranteed. So this is guaranteed. So the task is that we have to develop the TBD scheme, which guarantees a monotonicity preserving. So there is a theorem that suppose that the class of the nonlinear scheme, nonlinearity is a key essence for the high resolution shock capturing scheme. Schematically given by these equations, UN plus 1 I is given by UNI times the second terms and the third term, and C and D should be the function of the UNI, but it should be the nonlinear. And delta is described by the difference between I plus 1 and IA. And suppose that the nonlinear scheme is written something like this. The sufficient condition for the scheme to be TBD, total diminishing, is as follows. C should be greater than 0. D also should be greater than 0. Also, the sum of the C plus should be between 0 and 1. This is a condition to satisfy the TB total variation diminishing. Let's prove that. So first you calculate the UN plus 1, I plus 1 minus UN plus YI. Then if you plug this expression in here, you can write this equation, right? If we assume that this condition holds, here and here and here is a positive, right? So then, the absolute value of the left-hand side is, is the upper bound of the absolute value of the left-hand side is given something like this. The absolute value of the here, and this is the positive, this is a positive, and this is a positive, okay? This is a straightforward calculations. So let's calculate the total total variation total variation at UN plus 1. And definition of the TB n plus 1 is given by this equation. I runs through the minus infinity to the infinity. And if you plug this expression here, this inequality in here, so you can estimate, you can write down the upper bound of the TB at the UN plus 1, this given by this. Because I runs through from minus infinity to the infinity, these the terms is cancelled. These terms is nothing but the total diminishing at the time thrust of n, right? So then, so you can prove that so you prove that if this condition is satisfied in the class of the nonlinear scheme, and the TBD condition is automatically satisfied, then so you get the monotonicity preserving scheme, right? So therefore, if we invent a higher order scheme in this form, the scheme is a TBD if this condition is satisfied. Actually, the concrete formula of this Cn and Dn depend on your numerical flux scheme. And this is a concept for a high resolution shock capturing scheme for the scalar equations. So one example for high resolution shock capturing scheme, HRSG, high resolution shock capturing scheme is, this is just one example, monotone upstream centered scheme for conservation law, which is called a muscle or mere muscle. So let's define the volume average quantities as we did in the previously like this. And let's consider some profile inside the cell. So piecewise, in this case, we consider the piecewise parabolic cells reconstruction inside the cell. UX is a parabolic form. Then you can get this expression. So yeah, you can get this expression. And delta xu and delta second derivative of u is evaluated somehow. So here is the schematic picture for the cell of the I and I plus 1 over 2 and y plus 1 over 2. And if you directly calculate, okay. You just give the estimate delta xu at the I is the direct finite difference of this expression. Also, in this case, I don't need a delta x, sorry. This is a second order accurate expression for the delta xu and delta xxu. And if plug this expression to this, this one and evaluate this profile at the I plus minus 2, you get the left state, which is described as UL, left state of the variable given by without blue color region. Make sense? It just plug this expression to here and evaluate it at x equal I plus 1 over 2. Then so you can get this expression, okay, without a blue one. Also, so if you evaluate these terms at the I plus 1 cell here, and if you evaluate the distribution inside the cell at the I plus 1 over 2, you get the expression for the light state UR or something like this without blue colored terms. So, but as I explained that this finite difference or, the straight finite difference makes the oscillation or may causes oscillations. So we need to include the flux limiter as I demonstrated in the previous work, right, previous slide. So introducing the flux limiters, which is a function of the Ry plus minus, plus means that the plus case, the denominator, numerator is I plus 1, or for minus case, numerator is I minus 1, sorry. So as I explained, the flux, the limit the flux functions is reduced to 0 when the sign of the Ri is negative, right? In here, this region. Then so you can prove that this expression to the ui plus 1, which correspond to the first order upper window scheme. The meaning of this is just the left state at the I plus 1 over 2 is just copy from the I, and R state at I plus 1 over 2 is just from I plus 1 for at the discontinuity at the shock case. So the second and third terms is if the profile is smooth enough, and this limiter function is reduced to the 1, which means that for smooth profile, you can reconstruct at the cell interface value with a higher order, the higher order expression given by this expression. Phi is a flux limiter function. One choice is a mean mode function, as I demonstrated in 2 or 3 pages before. So this is a way or the scheme how to construct the physical quantity at the cell interface. So by using these the expressions, now the muscle scheme is given by this. And here is a volume average, the volume average the scheme, and in which we have to specify the numerical flux at the F tilde. And in mass scheme, the F tilde is given by this expression, right? Where the UR and UL is calculated, calculated by this expression. So for the A equals positive case, and F tilde I plus 1 over 2 is going to be A times L state at I plus 1 over 2. So if the flow is not smooth, like shock or discontinuities, UL is going to be reduced to the UI. So which means that this scheme is reduced to the first order upwind scheme, right? The things is similar for the negative A case. For negative A case, this scheme is going to be the A times UL at I plus 1 over L, 1 over 2, sorry. If the flow is not smooth, it's going to be the first order upwind scheme. So it doesn't depend on the sign of the A. It's automatically reduced to the first order upwind scheme. If the flow is smooth enough, then so UL or UR contains the information for the higher order profile. So then you can estimate or you can get the higher order numerical scheme. This is the essence for the mass scheme. So for the limit function in the example, I applied a min mode function as I explained before, something like this. So B should be as because of B, we want to this profile as large as possible, which means that B should be as much as possible. But there is a limitation in the range of the B. So what's the value of the B? So let's calculate this scheme by mass scheme by plugging this expression to directly here. So this is a messy, the messy expression of that, but you can easily prove that this scheme, mass scheme, is given something like this, right? And then so if you, for example, if you these terms, phi, upper phi argument value is Ri minus y times delta I is a min mode function times delta I, but because of the functional form of min mode function, you can easily, you can prove this combination is given by, is rewritten by this function, okay, min mode plus delta I plus minus 1. So by using this expression, you can rewrite this one, you can rewrite this one, and this one, and this one, and this one. Then, so finally, you get the, you get the mass scheme is given by this one. A minus A bar plus is given by this expression and times delta I minus 1, and A bar minus 1, A bar minus is given by something like this. So in Harton's theorem, I didn't put the name of the, but the Harton's theorems are here. Here, this is Harton's theorem. Suppose that the class of the nonlinear scheme is written something like that. This CD should be satisfied at this condition, right? So now, so we can use the Harton's theorem because scheme is reduced to this form, right? Let's compare this scheme and Harton's theorem scheme. So you can easily find that correspond between the C and A bar plus and D and A bar minus, right? So then this is a condition to get the total variation diminishing scheme. So now, so we can estimate what is appropriate value for the B. So the Harton theorem tells you that A bar plus and A bar minus should be satisfied this condition, should satisfy this condition, sorry. So when delta I plus delta I minus 1 is negative, also delta I minus 2 over delta I minus 1 is greater than B, the first condition is the strongest condition among these conditions, which result in the B should be between the 1 over 4. On the other hand, if the delta I minus 1 is negative, and delta I plus 1 over delta I is a positive, and the second condition here is the strongest one to constrain the B, and it gives B should be 1 over B should between the 1 and the 4. So now, so we know the range of the B to satisfy the total variation diminishing condition via the Harton's theorem. So now we know that which value we should choose B. But there is a freedom between the 1 over 4 and to which value is appropriate for your problem, we have to do a numerical experiment by changing the B. B equal 1 is the most diffusive case. Most diffusive may be the the safest case. And B equal 4 is a very aggressive case because you reduce if B equal 1, here is a profile something like this. If you increase a B equal 4, you shift this point to the left direction, right? Which means that you expand the phi equal 1 region as much as possible, but maybe B equal 4 is too aggressive. It depends on the model you want to solve. Okay, let's apply the master PPM. So now we have a scheme given like this. And UR and UL is constructed by this equation with a min mode function phi with the appropriate value of the B. Then so let's try to let's solve the discontinuity propagation problem. And here is the exact solution again in blue curve, black curves. And the blue dot curve is muscle PPM reconstruction scheme. The right-hand side is the reference for the first order upwind scheme. Again, which is better? Of course, left, right? You agree? Because discontinuity is correctly and sharply captured by this scheme. At the discontinuities, this muscle scheme is automatically reduced the first order upwind scheme. But for smooth profile, it gives you the more accurate solution. This is the essence for the high resolution shock capturing scheme for the scalar field case. Sorry, do you have any question or? It's fine. Okay. So maybe I don't have to explain this one because yesterday I have already explained the system equations. But for one specific example, so let's consider that the Bala equations. So one direction equation case, the f flux is given by some constant a plus multiplied by u, right? So in that case, the characteristic speed is delta f delta u, which gives you the a is a constant, and the characteristic curve we learned yesterday, dx over dt is a. For the schematic diagram is not schematic. For the space-time diagram, this solution is given by these equations. Here is the initial profile, and you may have a discontinuity at x equals 0 and initially, but this information propagate to the characteristic curve dx dt equal to a, which is constant, which means that you have a bunch of the characteristic curve, and along these characteristics. The curves, every information propagate something like this, right? This is a propagation in the discontinuities. So what happens if you assume that f is a nonlinear function of the u, like u squared over 2? This is called Bala equations. So you can also calculate the characteristic speed by differentiate f in terms of the u, and it's going to be the u. And the characteristic curves become dx dt equal to u, right? Suppose that we give the initial condition like 1 at the negative x region and 0, discontinuity at the 0, right? Yeah. Then so what's going to happen for the Bala equation case? Because the characteristic speed is proportional to the u in the negative region. The characteristic speed is something like this. But the negative region, u is a 0, which means that the characteristic speed is 0, which means that the characteristic curve is something like this, right? This is a T-X plane. So which means that at some point, the two characteristics collide each other. Then so in this case, the shock wave appears. So this is the Bala example of the Bala equations, but as we have learned yesterday, so in system equation like Euler equations, sometimes this collision of the characteristic happens, which makes a shock, right? So the short summary of the lecture 2 is a finite volume method, and one first order upwind scheme is essential for the numerical hydrodynamics. But caveat is a first order upwind scheme is a diffusive. So second point, the Godunov theorem says that there is no monotonicity preserving linear scheme, which is a second order or high order argument, which means that we have to, or it is necessary to invent a monotonity preserving nonlinear scheme. And one example is introducing the flux limiter to make the flux nonlinear. And the Maslow scheme is one example. This is not the unique solution, just one example for the high order monotonicity preserving scheme. So now we know how to handle the scalar equation, which may contain the discontinuities, right? This is the scalar equations. Okay, let's jump into the system equations, Euler equations. And so the problem you try to solve yesterday is one example for the Godunov method. But it is infeasible to solve the Riemann problem generally from the computational course. So we need to find a numerical scheme for the hydrodynamics. And one example is a law method. A law method is one of the representative methods for the approximate Riemann solver. And let's linearize the Euler equations. Linearize means freezing the Jacobian matrix freezing means that A doesn't depend on the location of the X. So this conservative form is written by this equation where A is just Jacobian, partial F, partial U. And the important property is A is homogeneous in the sense that F is multiplied by the A times U. By the way, U is a conservative value and F is a conservative flux, right? And the law proposes matrix A tilde, which satisfies the following condition, is good enough to capture the solution for the discontinuities. A tilde should be satisfied, one, for the limiting case for the L and R state at the interface, it's going to U. A tilde is going to the original matrix A, matrix A, given by this equation. The condition 2 is for an arbitrary L and L state, the flux difference FL and FR and FL is written by the A tilde times UR minus UL. The condition 3 is the eigenvalue vector of the A tilde is linearly independent. The condition 1 and 3 sounds very natural requirement, right? Because if you want to take the limit to the UL out to the U, the A tilde should be reduced to the original Jacobian matrix. Also, to guarantee the linear independency, the eigenvalue of the A tilde should be the linearly independent. So what's the meaning of the condition 2? So the condition 2 is actually related to Rankine-Hugoniot relation, which is essential to capture the discontinuities, which is given by the characteristic speed plus the difference behind and after the shock and the flux as well. This is called the Rankine-Hugoniot condition or jump condition or shock condition. So we diagonalize a matrix A tilde such that light eigenvectors of the diagonal matrix of the lambda tilde. Lambda tilde is a diagonal matrix for the characteristic speed of lambda 1, 2, 3, and left eigenvectors, vectors, something like that. So that this condition implies, not exactly, but it means that if this condition is satisfied, the Rankine-Hugoniot condition is satisfied as well. So law scheme is given by like this. Here is a finite volume expressions, and the numerical flux is given by the flux at the grid index I and flux at the cell I+1 times this correction term. And this correction term, A tilde, the absolute value of the A tilde is given by the right eigenvector and diagonal matrix and left eigenvector, right? So before going to the detail of what's the complete the expression for the A tilde, let's consider why this scheme works. So suppose that Jacobian matrix and eigenvector are frozen. Frozen means that it doesn't depend on the time and the space. By starting these expressions by multiplying the left eigenvector from this equation, so frozen condition mean that you get this expression, right? This is very straightforward. Because A is decomposed to the R times lambda to the R minus 1 and the diagonalized diagonal matrix, then so you get this expression. R minus U plus diagonal matrix times delta X R minus U. So here's the expression for the, sorry. So here's an expression for the low method. So do you understand what's the meaning of this equation? Here is a lambda is a diagonal matrix. So this is nothing but this 3 scalar equation for R minus 1 U. So we know the numerical scheme to get the high accuracy solution even in the discontinuity exists. So now, so we can apply this scalar, the scheme developed in the scalar case to the system equation by using this equation, by utilizing this equation, right? So yes, and then so the first flux with the first order upwind scheme or muscle scheme is given by the flux is given by these equations, right? Sorry. Oh, yes. Okay, let's start from. Give me 1 second. Yes, right. So sorry. And so the first order scheme or high order, first order wind scheme is given by these equations and by multiplying. Lambda is now characteristic speed, and here is a conservative quantities, and lower U in scalar case, and this is a. Okay, this is just expression for the scalar case. Sorry, where is my expression? Anyway, okay, if you take the R and UL to the I plus 1, I plus 1 and I, it's going to be the reduced to the scalar first order upwind scheme. So you have a characteristic speed of A and absolute value of the characteristic speed of A. This is the expression is equivalent to system case by this expression, right? Lambda is a diagonal, but it contains the information of the characteristic speed. Okay, agree? Then so, okay, I have written this one. So if you multiply the right eigenvector from this equation, you get this one, right? So then, so the R lambda R minus 1 U is given by these equations, right? And because of the homogeneous properties of the matrix A, F is multiplied by A, is given by the A multiplied by U. A is diagonalized by lambda times the right eigenvector and the left eigenvector is something like this, which means that this quantity is equivalent to the F, the flux F tilde. So this expression is rewritten by this form by using these properties. Numerical flux at the interface should be given by the arithmetic average of the physical flux at the I and I plus 1, plus some information from the characteristic speed. So this is nothing but the numerical scheme for the low scheme. I hope you understand why this scheme works compared by comparing the scalar field case, right? So now we are now in a position to evaluate the A tilde concrete form of A tilde. So A tilde is decomposed to the right eigenvector. Sorry, this is not lambda tilde, and left eigenvectors. Let's define the parameter vector W given by the lower W 1, 2, 3. It's a square root rho, square root rho U, and square root rho upper H. Upper H is a specific entropy defined by the E plus P divided by rho. So now the U is a rho U, and E, and energy is written by this parameter vectors. It's a straightforward. It's something like this, and the flux of the F is written by the lower W1, 2, 3 is given something like this. This is a straightforward calculations. And let's define the delta Q is the difference between the QL minus QL. Also, the Q bar is the average of the QL and QL. Then, so if you calculate the delta U by plugging this expression, this delta is acting like a differential operator, and you can get this expression, right? So W1 is the root L and root L or root L. So here, so you give the combination for the bar, W1 bar and W1, right? This is a straightforward calculation as well. So if we define the B matrix something like this, so you can write down the delta U is B times delta W. Okay, so now you know that expression for the delta U, and the delta W is given by these equations, so you can get the matrix of the B, right? B plus delta W gives you this expression. You can also do the similar things for the F flux difference delta F, and matrix C. This one gives you that this delta F multiply W. So now, by delta W is a sort of the parameter. So now delta F is the matrix C inverse matrix B times delta U. So the condition is the 2, which should be satisfied for the Rankine-Hughes relation, is that A tilde is given by the C times B inverse matrix of the B. So the concrete expression for C inverse B is given by these equations, and U1 bar is by this expression. This is just the definition. So let's introduce the low average. Low average denoted by the bar. Low bar is a combination of low L and low R, and U bar H by defined by the L and combination of the L and R state. Then so the A tilde or CB inverse is gonna be reduced this one, right? This functional form is nothing but the Jacobian matrix for the original equations. So we can easily the condition 1 and 2 are satisfied if the L and R and L state is reduced to the U. This expression is going to the original Jacobian matrix. And the eigenvalue vector is linearly dependent, and by calculating the diagonal matrix of by diagonalizing this matrix, it gives you that characteristic lambda matrix. So the left and right eigenvector is given by this one, by this expression, and here is the eigenvalue vectors. The point is that they should, lambda 1 or these quantities depend on the U, CS, rho, and P, and so on. But these quantities should be evaluated with low average. Low average means here, right? This is a low scheme. Then so after evaluating the R minus 1, lambda 1, you plug them into this equation, right? To get the numerical flux of the cell interface I plus minus 1, 2. This is a first order print scheme with a low scheme. And to make it a higher order is straightforward as we run in the muscle scheme. First, you construct the higher order L and R state by using this expression with the flux flux limit function phi. Then so now you have a higher order U expression for the UR and UL, and then you calculate low average of the U bar, H bar, and rho bar, also these expression. And then so you can evaluate the flux, physical flux at the L and R and L state, and also here it's a low matrix. This is a higher order for the scheme for in the low method. So the other method is okay. Low scheme is a very robust, and it looks physically it's nice. But the point is that to calculate the right eigenvectors and the left eigenvectors, I implicitly assume the gamma rho equation of the state, because you need the information of the CS. CS is the sound speed, and also the calculated this bit messy matrix. It is not necessary, but if you assume the gamma rho equation of state, it's straightforward. But if you don't, it's not straightforward. It's really messy things. So for test problem or simplified situation like a gamma rho equation of state, low method could be the best. But our target is a more complicated system, like equation of state is given by the tabulated equation of state based on some particular nuclear physics theory. So in that case, calculating the left and the right hand eigenvector is not straightforward, which means that the low method is compatible, but how to say, the affinity is not so high in the scientific target case. Well, how should I avoid that? You know, there are a couple of methods to approximate Riemann overlap, which doesn't require the composition for the right eigenvectors and the left eigenvectors. One example is a HLL method, and described by this scheme, and this is nothing but the finite volume method. But the numerical flux of the F tilde X is given by this condition. So here is a space-time diagram for again. So you have a left propagating wave and right propagating wave, because we know this system has a 3 characteristic velocity. The left, the left propagating the characteristic speed is calculated by the lambda minus u minus cs this direction, and by this equation. Also, the right propagating the characteristic speed is given by the plus lambda plus u plus cs by these equations. So in HLL scheme, so we learned that so there is a contact discontinuity between them and inside the Riemann form. But in HLL scheme is completely ignores the internal structure of the HLL of the Riemann form. So it gives you that if this lambda L is positive, the flux should be the flux, physical flux at the AL. So the meaning of this this condition is, here is just one specific case, but if lambda L is a positive, which means that the Riemann structure is something like this: lambda L, lambda R, and intermediate state, right? So we want a solution from starting from this initial condition. So with certain time, this state should be the left state, right? Then the solution is something like this. On the other hand, if the lambda R is negative, the opposite side, this form is become something like this. So the solution should be the right state at the initial. So in the middle, so the HL flux is given by the combination of lambda L, and the R and the L state. So I have 5 minutes. So I will prove how do you get this result? How do you get these expressions? So let's start from this space-time diagram. You have a left propagating wave and left state, and light propagating state, and here is a light state. And here is an unknown HLL. HLL means that the name of the author, Hart and Luxley. So in HLL state, we assume that the Q conserved quantities at the time, at certain time, is given by the Q bar L for the lambda and Q bar HL. And Q bar R, lambda R is a negative case. And Q, okay, yeah. And the basic equations is an Euler equation, like something like this. So integrate, if you integrate for between the t, for the t between the 0 to the upper t, and x between the xl and xl, which means that you integrate these regions, something like this. Here is t, here is xl, here is xl. If you integrate this the space-time by these equations, it's easy to get right, left, q or tx is given by left, right, initial state, plus flux term to 0 to right? Just integrating these equations. Then so you can now construct x, you can calculate that. Okay. The next task is to evaluate the left term in here to here, because we know the propagation speed, and here this is given by lambda L plus time multiplied by lambda L multiplied upper t. Also here is the position is lambda L multiplied t. So if you integrate this one along here to here, so you have a three region, here to here is L state, and here to here is a HL state, and here to here is a R state, right? So then, so the right-hand side is given by this. Okay, just evaluating this equation along with this one, right? So from this expression and this expression, the first term is canceled out here. This is a cancel out. No, sorry, not one. This one. Then so you can calculate the HLL state for the conserved quantities. Should be written by this one. This is a HLL state in this case. The final task is to calculate the physical flux, numerical flux in the HLL state. So again, so we integrate this equation, but not from here to here, just from here to here, only the negative x regions. Then so you can repeat the same calculations, and finally, so again, the left-hand side is just calculate, right-hand side is calculate the volume, space and time integral with these equations. On the left-hand side is just calculate the distance not from here to here, right? We have a left state and HL state, which correspond to the left state and HL state. Right? So then, so you now plugging this expression to here, you can finally calculate the numerical flux of the FHL state. Yeah, this is the expression for this one. So this scheme is completely ignores the internal structures of the Riemann form. Also, these schemes more used to the more simplified. So let's forget about the L and the light state, something like this. So this is called the HLLE schemes. So you only take into account that this propagation speed. You don't have to worry about the L and R state. So you don't need the if conditions to evaluate the the numerical flux F. Surprisingly, it's going to be more reduced to the simplified one. So let's take the maximum value of the maximum absolute value of the left and right speed, the propagation speed. So this Riemann form is simplified by like this in this case, right? Then if you plug this lambda to this expression, so it's reduced to the very simplified one, right? This is called the local Lux fluid or LLF scheme. And then so now is a lunchtime. The exercise today is let's develop an approximate Riemann solver from scratch to solve the SOD problem. And here's a density profile SOD problem for exact solution with black curves. And the green one is a PPM method with, I don't remember which Riemann solver I used to make this plot. But anyway, you have a couple of options. For example, for the Riemann solver, you have 4 options. Low is most robust, and the HLE and LLF is a more cheaper Riemann solvers. And also sorry, I didn't put the name here. It's a reconstruction scheme. Reconstruction means how to calculate the L and R state at the interface. Here, this one. The construction scheme is you have the most simple one is forget about the second and third terms, which gives a first order scheme, first order reconstructions, and more accurate scheme is going to be the piecewise parabolic method, PPM method, by specifying appropriate limiter functions. So you have a couple of options. So I recommend you to start from the very simplified one, like maybe local lux freely, LLF is a most simplified one, and first order cell reconstructions. And you can compare the exact solution to your numerical simulations. And for example, if you change the reconstruction scheme from the first order to the PPM, the solution should be accurate, should be more accurate than the first order scheme. Also, what's difference between the employed Riemann solver? This is a good demonstrations. And this is an exercise for today. Yeah. And now is lunchtime, I think. So do you have any question or comment? So by the way, I have already uploaded this slide to the Google document. So during the tutorial, please look at this information or lecture notes. Okay. Any question or comment? Okay.